Something impossible just lit up our skies, and it isn't drifting, it's aiming. On July 1st, 2025, a streak the color of cold iron slipped out from the glare of the galactic center, and our instruments caught it for the briefest heartbeat, like spotting a shadow move at the edge of a door you swore was closed. The system flagged the trajectory as wrong in all the right ways, retrograde against the clockwork of our planets, steeply tilted and so straight it looked less like an orbit and more like a decision. Within hours, telescopes across 6 continents spun toward the same point. Within a day, the chatter on private science channels turned from weird comet to interstellar third confirmed. But that word didn't capture it. This visitor wasn't just fast, 245,000 kilometers fast, 4 times Voyager's stubborn crawl into the dark. It was old. The early draft age estimate landed like a punch, maybe 7 billion years, maybe older, a relic from before Earth cooled, before our oceans learned the taste of oxygen, before our sun even settled into its long, steady burn. You don't casually meet something older than your world. You don't expect it to be headed straight past your front porch with the kind of poise that makes chance feel like a flimsy excuse. And you definitely don't expect its thin fog of dust to defy sunlight, streaming not away from the star that's heating it, but toward it, as if the object were shedding heavy grit against the pressure that should push it back. Natural. Maybe. Convenient, not even a little. The SETI dishes woke up like a city roused by sirens, narrowband scans, wideband sweeps, dumb luck listening and clever algorithms hunting for patterns that don't belong to rocks. In the first week they hoarded a mountain of data, enough to drown in if you don't know how to swim, and the questions multiplied faster than answers. Why was it hidden for weeks in the brightest, most crowded slice of the sky? Why the razor-thin timing that gives us months of inbound observation, and then at the exact moment we'd want eyes the most, a perfect solar blackout on October 29th, when the sun itself blocks our view. You don't need to be an astronomer to feel the tension in those dates. If you wanted to slip past a noisy planet without being seen making your biggest move, you'd do it there then. Maybe it's a fluke. Maybe it's physics playing dice with a grip. But here's the part that keeps people staring at the ceiling at 3 a.m. For a century we've been shouting into the dark with radio and TV and radar pings, a growing bubble of artificial noise now 200 light years wide. We beamed a deliberate hello with Arecibo. We stapled our names and anatomy to spacecraft and tossed them into the gulf like bottled messages. If anyone has been listening, they've had time to hear the static map the source and decide whether the little blue spark has learned to answer its own questions yet. So when a mountain-sized object from the galaxy's thick, ancient disk swings in on a path aligned with the plane of our worlds, skimming near Venus, near Mars, near Jupiter, at distances so precisely coincidental, you can measure their improbability in fractions of a percent. Even the most cautious minds allow a second thought. This is where the story gets dangerous and delicious, because the line between sober science and electrifying speculation is razor thin, and crossing it can make you look foolish or prophetic. The responsible thing is to say unknown and gather data. The honest thing is to admit that unknown has a gravity of its own. And the thrilling thing is to wonder if this is how first contact actually feels. Not with trumpets and landing lights, but with a quiet ancient traveler that has learned the most powerful language in the universe, time. If you've ever stared at a night sky and felt small, hold on to that feeling. We're about to learn that small can still be seen, still be heard, and maybe, just maybe, still be chosen. Stay with me. We're going to peel this apart. What was seen, how it moves, why the age matters, what the silence might mean, and what could unfold when it slips behind the sun, where our biggest eyes can't follow. If this is only rock and ice, it will still rewrite how we search the void. And if it's not, if it's something crafted, guided, or carrying a message, we may already be part of the conversation. Thought that the first clue wasn't a bright smear in the eyepiece. It was a math problem no comet should solve. On July 1st, 2025, the ATLAS survey in Chile flagged a fast mover slipping out of the glare near the galactic center, where the sky is so crowded with starlight that even obvious things can play invisible. The track looked wrong in a way that made astronomers sit up straight, hyperbolic, not bound, retrograde, running against the traffic of the planets, tilted almost upside down to the ecliptic, and so straight that the orbit read more like an intention than a curve. Within 24 hours, the alert rippled across observatories on 6 continents. Amateurs combed old frames from early June and found mist streaks buried in the Milky Way's glitter, and the Minor Planet Center gave it the label that changes the tone of every conversation. 3/3 interstellar. The difference this time was timing. Oumuamua was a ghost, we noticed after it had already waved goodbye, and Borisov, though active, gave us a narrow window on its outbound arc. This one was caught inbound, months before its closest pass, which is the observational equivalent of getting a front row seat before the curtain rises. The first images showed a nucleus wrapped in a whisper of dust, barely a coma, like a breath-fogging cold glass. Then something stranger, hints of a tail that didn't obey the simple rule every comet follows in schoolbook diagram. Instead of streaming neatly away from the sun, part of the dust seemed to line up toward it, as if heavier grains were being thrown forward against radiation pressure rather than pushed back by it. Natural explanations exist: large particle sizes, peculiar ejection angles, crusted surfaces that vent in odd jets, but the anomaly was enough to put every big eye on it. By the second day, 2022 observations from 31 observatories had tightened the solution, and the numbers got jaw-tightening. Perihelion speed, near 68 km/s. Relative to Earth, a closing velocity brushing 98 km/s. Overall cruise on the order of 25,000 km/s, 4 times Voyager's proud plod into interstellar night. An eccentricity above 6, a cosmic bullet rather than a boomerang, and that steep retrograde tilt near 75°, meaning it was coming at the solar system like a salmon fighting the stream rather than a leaf drifting with it. All of this would be enough to call a fire drill in the sky, but there was one more detail that changed the mood from curiosity to urgency. The approach vector had been masked for weeks by the brightest, messiest patch of sky we can point at. Against that backdrop, an object this fast can hide in plain sight until it's nearly on top of you. Coincidence is fair, calculated concealment is spicy. Either way, nobody wanted to be late again. The SETI community pivoted in hours: narrowband sweeps for engineered tones, broadband checks for anything that smelled like modulation, and a rolling harvest of spectrum that piled up into tens of terabytes by the end of the first week. You don't collect that much data unless you believe there's a nezzo chance of hearing something that talks back. Meanwhile, dynamicists ran the film in reverse through the galaxy's gravity and came back with a hint that made geochemists lean in. A velocity signature consistent with the Milky Way's thick disk, the older, puffed-up population whose stars are lean on heavy elements and fat on time. If that association holds, 3I isn't just foreign, it's ancient. Possibly older than Earth by billions of years, a relic that remembers when our sun was still just an idea in a molecular cloud. That's the kind of age that turns a rock into a wreck, and the calendar adds a twist worthy of fiction. On October 29th, at the exact moment when solar heating should be at maximum and any unusual behavior would be most revealing, the sun itself will sit squarely between us and the visit, blinding our best telescopes and muting our curiosity for weeks. You could call it bad luck. You could call it perfect cover. Either way, the clock is running. The world is watching, and discovery is just prologue. Next comes the part that decides whether this is merely the fastest snowball we've ever met, or the first deliberate knock on the door. Thoughtful. Speed is supposed to calm down as you get closer to the sun, Gravity trades distance for velocity in a neat, predictable way, and orbital paths bow into curves you can sketch on a napkin. 3IATLAS refused the napkin. From the first refined solution, the numbers read like a dare, an eccentricity over 6, which means not just unbound but wildly so, a solar flyby speed near 68 kilometers per second, a closing rate with Earth that hovers around 98 kilometers per second, and a cruise velocity that makes even our proudest emissaries look stalled, roughly 245,000 kilometers per hour, more than 4 times Voyager's pace into the dark. At that speed, your gut expects a long, lazy arc. What the sky delivered looked almost like a line. The path was so close to straight that even veteran observers found themselves double-checking plate solutions, wondering whether a hot pixel had learned how to sprint. It hadn't. The orbit is real. The geometry is brutal. Retrograde by about 75 degrees. It's driving head-on through the planetary freeway, not riding with it. Tilt the ecliptic like a dinner plate. The planets skim the rim in the same direction. This thing knifes across the plate in reverse, almost flat to the surface, turning every meeting into a high-energy close pass. That's why the relative speeds look absurd. The Earth is doing 30 kilometers per second one way. Atlas is bombing through the other way. Stack those vectors, and you get a closing speed that laughs at intercept plans. Chemical rockets? Not a chance. Even if you launched yesterday, even if you threaded a perfect gravity assist, you'd still arrive at a blur. Instruments designed for civilized flybys at 10 or 15 kilometers per second don't love it when the target whips past 6 times faster. You don't image, you blink and hope the CCD guesses what it saw. When you push past the headlines, the velocity tells a deeper story. Objects don't wake up fast, they get fast by time and luck, by grazing deep gravitational wells and taking the slingshot every star offers, by surfing the galaxy's potential like a longboarder catching every break. Dynamics folks ran the tape backward through a model of the Milky Way's mass and came back with a fingerprint motion consistent with the thick disk, the older, puffier layer of the galaxy, where stars tend to be lean on heavy elements and rich in age. That fits a traveler that's been on the road since before our oceans existed, maybe since before our sun existed. Every encounter adds a few kilometers per second. Every near miss sharpens the trajectory until you get a bullet that remembers the hands that loaded it, but not the gun. And then there's the way it arrived. Stage managed by the worst possible backdrop. Dune frames show faint streaks right in front of the galactic center's star swarm, where a million glittering points crowd the detector and smear away the obvious. If you wanted to hide a fast pebble in plain sight, you'd drive it through that glare. Is that malice or math? Nobody can prove intent from an approach vector, but even the most skeptical observers admit the timing looks like it picked the loudest room in the house to whisper in. The trajectory adds a second, stranger drumbeat, a near-perfect alignment with the solar system's orbital plane, but coming at it from the wrong direction. That geometry sets up a chain of improbable rendezvous, a respectful miss of Venus, a tighter pass near Mars, and a statistically spicy brush with Jupiter's domain. Individually, none of those distances turns heads. Together, and with that retrograde tilt, they read less like a drunk stumble through town and more like a route. If you're a naturalist at heart, you can still explain it. The galaxy is big. Roll enough dice and you'll eventually get a straight flush, but the math doesn't blink when you stare at it. The combined odds of the alignment and the timing aren't friendly. The result, though, is practical. Spacecraft already en route, Mars orbiters, deep space missions will get angles that Earth cannot, especially when the sun blinds our telescopes around perihelion. The speed also sets limits on what the object can be. Small things get spun up by radiation pressure and outgassing. Big things carry momentum like a religion. Early photometry hints at a nucleus that isn't tiny. Put that together with a coma that barely whispers, and odd dust behavior that sometimes points the wrong way, and you start building two very different pictures. Either an ancient crusted relic that vents in weird forward-thrown jets because its surface is armored and its particles are heavy, or a body that does not play by the thermal rules because something besides sunlight is telling it how to breathe. No one is stamping either conclusion. What everyone agrees on is the homework. Spectrographs to sniff composition, radar if we can steal enough signal to noise, relentless light curves to catch rotation and tumbling states, and a wall of radio monitoring to rule out the one explanation that would turn a curiosity into an ear, because buried inside that velocity is a practical question with a sharp edge. If you can get this fast and still thread the ecliptic like a needle, you can choose where to look, and if you can choose where to look, you can choose when to hide. The numbers got us here. The chemistry will decide what kind of thing we've actually met. If speed wrote the headline, age writes the plot twist. The motion fingerprints point to the galaxy's thick disk, the older, puffier population where stars formed lean on heavy elements, which means this traveler could be older than our sun by billions of years, possibly as ancient as the first bright cities of the Milky Way itself. Imagine a rock that remembers the galaxy before the spiral arms were well drawn, drifting for eons through starbirth nurseries and supernova ash, collecting scars the way tree rings collect winters. That age isn't just a brag, it changes what the surface should look like and how it should behave. Objects that old don't keep their volatiles the way fresh comets do. They bake, they crust. They grow a sun-burnished armor that throttles the easy, pretty outgassing we expect. That helps explain why early images whisper rather than shout a faint haze where we'd expect fireworks. A dust stream that sometimes leans sunward instead of away, like heavier grains are being hurled forward by jets that punch through a pressure-hardened shell. It's a chemistry riddle wrapped inside a geology riddle, and both of them are engraved with time. Spectroscopy will be the lie detector. If the spectrum leans metal poor, fewer heavy element fingerprints than our backyard comets, then the thick disk pedigree gets teeth. If it shows exotic ices or unexpected organics, we learn what space does to fragile molecules over billions of years without the protection of a home star. And if something stranger pops reflectance curves with sharp engineered edges or emission lines that don't live in any natural catalog, that would be the kind of result that explodes Slack channels and keeps observatories awake on power they don't admit they're stealing. Even the mundane outcomes teach us something huge. The early universe's recipe written in minerals you can't cook up in a vacuum chamber. That's why teams are stacking instruments like poker chip. Wide field surveys will trace how the brightness wiggles with time, because spin states and tumbling tell you about interior stiffness. Tight, high-resolution spectrographs will sniff the coma for hydroxyl cyanides, carbon chains, sodium flares, anything that says this is a comet, just older, or this is a furnace you don't understand. Polarimetry will watch the light twist as it scatters, which reveals grain size and structure, the difference between fluffy frost and sandblaster grit. Even radar is on the wish list if geometry gives us a window, because radar splashes don't lie about size and roughness. Age also frames the weird tail geometry in a new way. A crusted ancient surface can trap gases until pressure builds, then vent through cracks like a miswired geyser. The thrust from those vents isn't romantic, it's directional. Vent a heavy slurry forward along the motion vector and solar radiation can't bully the grains back. They're too massive to sail. The result looks wrong to a textbook, but right to a battered relic, with buried pockets that finally found sunshine. And lurking inside that picture is a subtler point: thermal lag. Old dehydrated mantles don't respond instantly to sunlight. Peak activity can arrive offset from closest approach as heat soaks through rock and wakes whatever volatiles remain at depth. That delay creates odd maps of activity, and odd maps create odd momentum kicks. The difference between a natural kick and a guided nudge is small in the data, but massive in meaning. So the plan is simple: watch relentlessly and let the statistics outvote the story. Still, the age invites stories. If this thing was born in the thick disk, its parent system may be gone. Its star dimmed to a white dwarf or collapsed into something denser. It could be a shard of a planetesimal belt, shattered when a giant world migrated, or a comet core that survived multiple passes through someone else's glare before getting booted into the interstellar wild. Each scenario leaves chemical footprints, and the only way to read them is with photons caught now before the sun bakes the weak signatures flat. And yes, the silence matters. An object this old that still looks inert, no roaring gas, no wild coma fits the relic narrative. But silence also happens when something chooses not to advertise. That's why radio arrays are already humming. Not because anyone expects a hello, but because you don't get to miss the one time the universe chooses to clear its throat. So the stakes of Section 3 aren't about drama, they're about patience. Age buys you time to become strange. Time turns ice to crust, crust to armor. Armor to a puzzle you can only solve by catching light at the exact moment it leaves. If the spectrum says early universe chemistry, we've pulled a sample older than Earth without lifting a shovel. If it says common rock with uncommon behavior, we'll rewrite how comets age outside the protection of a home. And if it hints at anything that looks planned, regular modulations, discrete lines, surfaces that scatter like plates instead of pebbles, then the story we've been telling about lonely space gets replaced by a noisier one. Either way, the clock is running. The oldest messenger we've ever seen is warming up, and age is about to speak.
Thought for thought. It isn't just coming in fast, it's coming in wrong. 3IATLAS barrels toward the sun on a path that runs backward against everything else, slicing through the plane of the planets at an angle so steep, it's basically a dare, retrograde, tilted roughly 175 degrees to the ecliptic, and carrying an orbital eccentricity so huge the track looks like a near straight line. That would be wild on its own, but the geometry does something sneakier. Despite this backwards dive, the path lies almost flush with the planetary lanes, within just a few degrees of the same thin sheet where Venus, Earth, Mars, and Jupiter circle. Line up those facts and you get a move that feels less like a random flyby and more like threading a cosmic needle. The result is a string of close shaves that statisticians hate. Near Venus, near Mars, near Jupiter, each pass inside distances that make engineers reach for calculators and philosophers reach for tea. The odds of a truly random interstellar rock arriving on a retrograde trajectory, skimming the ecliptic, and timing 3 planet approaches this neatly, well under 1% by conservative estimates, and much lower if you multiply the alignments together. Yet here we are, watching the sky do math it shouldn't. And then there's the timing trick that makes veteran observers swear under their breath. Perihelion, the moment of maximum speed and maximum leverage, lands when Atlas slips behind the sun from Earth's point of view. That's a perfect natural blackout. Ground telescopes can't see it. Even space observatories designed to keep their optics safe won't point into the glare. For roughly 3 months, the most interesting object we've ever tracked will do whatever it's going to do on the far side of the furnace, with our eyes shut. If you wanted to perform a big maneuver without being seen, say a reverse Oberth burn that spends energy at peak velocity to dump speed and let the sun's gravity capture you, you'd pick exactly this geometry. Nature can produce coincidences, it rarely produces this many in a row. The physics here are clean and cold.
At perihelion, Atlas will be screaming past at around 68 kilometers per second relative to the Sun. Earth moves at roughly 30 in the opposite direction, so the drive-by speed difference if it came near us would be on the order of 98 kilometers per second, far too fast for any realistic intercept launched from our current pads. That locks in the strategy. Watch, don't chase. Use every vantage point that isn't blinded. Mars orbiters and rovers will have line of sight during the blackout window, so their cameras and spectrometers become priceless. Out near Jupiter, long-range instruments can stare into the dark and hunt for flickers of outgassing, odd polarization or brightness steps that look like rotation changes. Nature's signature is messy, but propulsion and deployment events leave crisp, sudden fingerprint. Even a tiny, deliberate delta V will skew the post-perihelion track in ways precision astrometry can catch. Meanwhile, the inbound leg has already served up strangeness, because the approach rides the background of the galactic center's star-crowded glare. Early frames hid Atlas in plain sight. That's camouflage by circumstance, sure, but it rhymes uncomfortably with the rest of the pattern. A stealthy direction, a blade-straight hyperbola, ecliptic alignment, and a solar eclipse curtain call at the exact moment when a speed change matters most. If the object is natural, the path still teaches us volume. It shows how the galaxy tosses debris into our neighborhood from the thick disk on tilted lanes, how gravity assists from long-forgotten stars can pump speed to absurd levels, and how often interstellar traffic probably skirts our system undetected. If the object is anything else, the path is the message. It reads our clock, touches our major planets without spooking our defenses, and vanishes into the sun's glare during the only window when a big move could happen without a global audience. Either way, this is the section of the story where geometry turns into motive. Every night between now and December is a chance to tighten the orbit solution, to learn whether the post-sun arc lands exactly where pure physics predicts, or wanders a hair off the rail. And should that hair exist, should the curve arrive a touch too bent or the spin rate notch in steps instead of drifting, then we won't just have an odd rock on our hands, we'll have intent. But that isn't the whole story, because path only hints at purpose. The next clue hides in the radio silence and the strange way its dust behaves when sunlight finally digs into the crust. It should be loud by now, closer to the sun. A true comet starts hissing. Water vapor rips off in jets. O sings at 18 centimeters. CN and C2 lines light up the spectrum, and the dust tail snaps away from the star like a streamer in a headwind. 3IATLAS refuses to play that script. The first deep looks show a coma that's there but muted, a teardrop haze wrapped tight to the core, and a tail that misbehaves, its brightest dust not fanning outward from sunlight, but edging sunward, as if heavy grains are being shrugged off in the very direction radiation pressure should lose. That isn't magic, it's physics with a twist. If you fling out millimeter-scale grit slow enough, think decimeters per second, the particle's beta factor stays tiny, so photon pressure can't bully them. That points to mass loss that's deliberate in cadence or buried under a crust that vents through throttled pores rather than geysers. Spectroscopically, the usual neon signs of boiling ices barely peak above the noise floor. Some nights you get wisps consistent with micrometer dust at a trickle of fractions of a kilogram per second. Other nights you get a flat line where there should be the breath of a waking nucleus. And then there's the light curve, a soft heartbeat with sudden tidy steps that look less like tumbling rock and more like facets catching sunlight for a beat before slipping back into shadow. Natural objects can do this, boulders, shards, fractured plates, but stepwise photometry always makes observers lean forward. While the optics squint, the radios are holding their breath. SETI spun up fast, narrowband scans, drift rate hunts, and transient sweeps across gigahertz of sky, harvesting petabytes in a week from the Allen array and piggybacking on time at other dishes. The easy wins would be a carrier tone that stays coherent as Earth turns, a repeating sweep that says intent, or bursty nanosecond spikes from electrostatic arcing on an artificial skin. So far, nothing that can't be blamed on our own RF junk or the sun's restless background. Silence isn't proof of absence. It can be a strategy. A probe that's been crossing gulfs for eons has learned patience, and if the galaxy really is a dark forest, you don't whistle while you walk. The absence of clear outgassing is just as slippery. There's a perfectly boring explanation. Billions of years in deep space bake a refractory rind. Cosmic rays sinter the outer layers. Micrometeoroids melt and seal pores. Volatiles retreat below a glassy crust, and heat leaks out through cracks so narrow the coma never bloomed. That can still kick dust. Big, heavy grains lofted by sublimation trapped under the crust, or by electrostatic lift when sunlight charges the surface. But the pattern here carries a whiff of rhythm. Dust speeds look constrained, not chaotic. The phase angle polarization is oddly tidy, hinting at surface textures that scatter light in ways closer to layered plates than to fluffy powder. Thermal measurements at mid-infrared don't show the dramatic day-night contrast a fluffy, low-density comet should flaunt. Instead, they tease higher thermal inertia, the kind you get from rockier or even metallic material. Again, none of this nails down built overborne, but every checkbox it ticks is one that natural comets tick less often. If you're hunting for smoking guns, you watch for non-gravitational acceleration after perihelion that refuses to fit a volatile-driven model. Tiny, discrete kicks instead of the slow, sun-linked drifts caused by gas jets. You search for spectral lines that don't belong in a comet at all, for example, narrow features from alloys or polymers, or a radar cross-section that's too specular for a rubble pile. You look for timing that's too clever by half-spin state changes that happen in neat increments, or brightness flares that repeat with clockwork precision. Mars is the ace in the sleeve. While Earth bakes in solar glare, orbiters and rovers can keep staring. A few images a day, a trickle of spectra, maybe even a whiff of dust composition, as sunlight scatters through the coma from their vantage, just enough to catch a glitch in the curve, a kink in the path, a hiccup in the spin. Back on Earth, we keep the radios open and the algorithms hungry. If it talks, we'll hear it. If it thrusts, we'll measure it. If it stays ghost quiet and rides pure gravity, the post-sun arc will still tell tales. Trajectories have tells the way poker hands do. That's the uncomfortable beauty here. Either we're watching a devolatilized relic behaving like a veteran traveler with a scabbed-over skin, or we're watching something that knows how to keep its profile low until the curtain of the sun gives it cover to act. And if the dust's odd cadence and the radio hush are the first hints of intent, the deeper hint is older, baked into the object's very motion through the galaxy, an origin story that stretches back before Earth existed, and that's where the trail leads next. Thought for 11. There's a window coming that keeps mission planners awake at night, and it isn't just rare, it's almost theatrical in how perfectly it lines up. On or about October 29th, when 3IATLAS swings through perihelion roughly midway between Earth and Mars, the sun becomes a curtain, and we, the audience, lose sight of the stage. For almost 3 months, every ground telescope on Earth and even our crown jewel orbiters will be locked out by glare. That blackout would be inconvenient for any comet. For an object on a retrograde path, tilted to nearly mirror the ecliptic, a path that already threads suspiciously close to Venus, Mars, and Jupiter, it's a gift. Because if you wanted to change your fate in a gravity well, you'd do it then. At perihelion, speed is king, and the infamous reverse obith play leverages that speed to burn against motion and shed a shocking amount of energy for the same push. Natural comets can't time thrust, they vent when they heat, but a system with even modest propulsion could break hard in the solar furnace, bleeding velocity just enough to fall captive to our star and park in a long, patient orbit. Add the sun's glare and the geometry, and you've scripted the one moment when a course correction would be both maximally effective and maddeningly hard for us to witness. That's why Mars is suddenly the most important observatory we have. While Earth stares into daylight, fleets at Mars, silent workers that were never designed to play sentry, will have clean angles on the post-perihelion arc. A handful of outer system craft will too, each with their own sliver of sky and limited time on target. No one is promising glossy images at closing speeds that brush 98 kilometers per second relative to Earth. Even a perfect camera becomes a stenographer, catching one letter of a sentence. But astrometry doesn't need pretty, just precise. If the path after perihelion bends by hairbreadths that volatile jets can't justify, if the non-gravitational term appears as discrete pulses instead of a smooth solar-linked drift, it won't matter that we missed the act. The footprints will still be warm. Here's where the numbers get itchy. An object arriving essentially head-on to the solar system's traffic, skimming the orbital planes to sample Venus here, Mars there, and then grazing Jupiter's sphere of influence, sounds like a tour stitched together by celestial chance until you stack the probability, the aggregate odds of those distances and timings lining up just because, are tiny, far from impossible, but small enough to make sober astronomers mutter. And the tail behavior we've already seen doesn't soothe anyone. A heavy grain plume that leans sunward hints at controlled mass loss or a sealed skin that vents through throttled cracks, the sort of steady, low beta shedding that can double as microthrust without flashing a neon sign. It looks like restraint, then there's the silent. The Allen array and friends are still combing terabytes of narrowband and wideband data, chasing the telltale drift of a carrier or the crisp comb of a digitally carved signal. It could be there and buried under the sun's tantrums. It could be absent because the builders of Atlas learned the first rule of survival in a crowded, unfriendly sky. Don't shout. If the galaxy is a dark forest, nobody yells hey and expects a hug. So the plan is simple and stressful. Triangulate from Mars, steal glances from the outer system, run photometry like a metronome, and let the math do what human eyes can't. Meanwhile, a second danger and opportunity runs in parallel. If 3IATLAS is shepherding anything smaller, daughter craft tucked into its coma, sensor seeds that don't need to be bigger than a suitcase, perihelion is the perfect place to let them slip free. Those would be invisible from Earth while the sun blinds us, and by the time we regain our view, they'd already be scattering along transfer arcs toward worlds of interest, faint as sparks carried off on a wind. Most of the time, this is where the sensible explanation wins. A battered relic with a glass-hard rind holds its breath until heat fractures the shell, then releases big, lazy grains that don't care which way photons push. Mars watches nothing more dramatic than a turn and fade. The post-sun fit accepts an outgassing model, nobody gets a headline, and the third interstellar visitor folds back into the natural catalog. But the scenarios that won't let go, the ones that keep threads of possibility tugging at the mind, read like this. The post-perihelion track comes back a shade too circular for a pure fly-through. The light curve ticks in steps like facets catching the sun in a timed sequence. The radar echo, if we're lucky enough to snag one, looks too specular for a rubble stack. A tight band signal flickers and dies in a way that seems almost shy. We're not betting on it, we can't, yet the timing, the geometry, the hush and that perfectly inconvenient eclipse add up to a test we can't ignore. Or that we learn how a truly ancient, thick disk wanderer behaves when deep time has scabbed it over and made it stingy with vapor, or we watch something old and careful break behind the sun and choose to stay. And if it chooses to stay, the next questions aren't academic. Where does it circle? What does it sample? When does it speak? The clock to perihelion is already ticking, and whatever happens behind that glare will decide which future the rest of us have to live in.
Thought for 20. If you want the line between weird rock and somebody's hardware to stop being a blurry rumor, you have to talk about proof, not vibes. And that's where the hunt around 3IATLAS turns brutal and precise. Start with the quiet. A real transmitter doesn't shout, it whispers in patterns. The Allen dishes and partner arrays aren't just waiting for a sci-fi hello. They're scanning for narrowband tones thinner than a piano string, and for comb-like spectra with teeth spaced so evenly only a clock could carve them. They watch for Doppler drift that slides with the object's spin and speed in a way chemistry can't fake. They look for polarization tricks, for signals that stay locked to a plane like a tuned antenna would, not the sloppy randomized polarization of dust and plasma. Then there's light itself. If the surface carries panels, radiators or plates, specular glints behave like a tell short, repeatable flashes that hit exact intervals as rotation brings a facet into the sun. Natural rubble sparkles, sure, but it doesn't keep time. Photometry teams are already treating the light curve like a heartbeat, searching for beats, harmonics and sidebands that imply active attitude control. A tumbling comet gives you a messy, quasi-periodic rise and fall. A stabilized bus gives you crisp steps, flat tops and phase-locked sequences. Radar would be a knockout punch, but at these ranges and speeds, you only get a razor-thin window, and even then the return is faint. Still, a single ping that comes back too mirror-bright or too sharply bounded could change the conversation in one night. Spectroscopy is the other blade. Natural comets shout water, CO, CN, OH, sodium. If Atlas keeps shrugging at those lines while showing odd metals, ceramics or volatiles that don't belong at its temperature, eyebrows go up. Conversely, a faint, sun-facing dust plume full of heavy grains could be either crust cracking or controlled mass dump used as propellant without ion engines giving themselves away. That's the game. Every natural explanation has a technological twin. Non-gravitational acceleration, sublimation can do that, but it should track solar heating smoothly, not jump in discrete pulses. Tail orientation. Radiation pressure should push it anti-solar, unless grains are huge, or unless someone is choosing what to shed and when. Even the silence cuts two ways. A truly cautious probe stays radio dark, uses passive sensing, and rides the sun's glare like a cloak. A truly exhausted comet stays quiet because there's nothing left to vent. So teams build traps for both. Occultation campaigns time the moment Atlas blinks out starlight as it passes in front of background suns. The depth and shape of those blinks sketch its outline with kilometer precision, and any sudden extra blinks nearby could reveal hitchhiking daughter object. Thermal images look for hotspots that migrate like powered components rather than static sun-warmed patches. High-cadence surveys stack thousands of frames to catch micrometeoroid-like fragments peeling away on clean transfer arcs, a signature of deployment, not fracture. Meanwhile, statisticians hammer the trajectory. They aren't arguing feelings, they're stacking priors. Retrograde at A1-D5 to shoot, ecliptic hugging, close sweeps of multiple planets, perihelion during an Earth-blind interval. Each is fine alone. Together they start to feel like a plan, but extraordinary claims don't get a shortcut. That's why the checklists are ruthless. Does the post-perihelion path require thrust beyond what measured outgassing can supply? Do light curve harmonics stay phase coherent over weeks like a controlled spin would? Do we see spectral lines clustered in ratios that scream alloys, not ices? Is there a carrier hiding under the sun's radio tantrums that drifts with Atlas, not with the solar wind? And because the universe loves to prank us, every yes needs independent replication from another instrument, another hemisphere, another pipeline. There's a human question threaded through the math, and it's louder than any signal.
even if we catch a pattern that looks engineered? Do we answer? The safe play in a noisy galaxy might be to listen hard and speak softly, if at all. The bolder play is to bounce a whisper off Mars orbiters or outer system relays post-perihelion and see if anything blinks. Both paths carry risk. A reply could be a gift, a shrug, or a door closing. For now, the best move is discipline. Keep cameras rolling from Mars while Earth is blind. Keep slicing radio data for combs and drifts. Keep modeling non-gravitational pushes with boring, honest physics, and refuse to let hope or fear bias the fit. If Atlas is ancient ice, the curves will settle, the spectra will bloom, and the tail will finally behave. If it isn't, it will betray itself in the one place technology can't hide: timing. Systems keep time. Rocks don't. And if timing turns out to be the smoking gun, then the next piece we need is the oldest one of all, what it's made of, and what that chemistry says about where and when this traveler was born. Circle the date that shouldn't matter, but suddenly does. When 3IATLAS swings past the sun at its tightest point, it does it while Earth is blind, tucked into the glare where even our sharpest eyes are forced to look away. That's not superstition, that's geometry doing a magic trick. For roughly 3 months, the thing everyone wants to watch most will be perfectly positioned where our ground telescopes can't chase it, and our flagship space observatories won't dare point. Perihelion in the shadow of the sun is more than a calendar entry, it's a window you could drive a plan through. If you wanted to hit the brakes without an arding, that's when you'd do it. The old classroom term is the Oberth effect. Fire your engines when you're moving the fastest, and you squeeze the most change out of every drop of propellant. Flip that logic into a slowdown, and you've got a reverse Oberth. Bleed speed when the kinetic energy needle is pinned. Do it right, and a visitor that should slingshot past us forever could be coaxed into staying. Do it there, and nobody on Earth can watch the burn. Natural comets don't perform. They vent, they hiss, they brighten with a messy rhythm that follows heat, not strategy. But this object has been stingy with spectacle, hinting at dust and barely a whisper of gas, while shrugging off the dramatic tales textbooks promised. If it stays quiet through the approach, and then during the blackout its path after perihelion bends too much to be blamed on weak outgassing, we're in new territory. A curve that can't be paid for by sunlight and ice has to be funded some other way. And yes, astronomers have the receipts ready. Before the blind period, they measure the momentum to the decimal. After, they measure again. The difference tells the story. Meanwhile, there's a second stage to this that makes professionals tap their pencils. Alignment. 3 close passes in a single tour. Venus, Mars, Jupiter are the sort of route you'd pick if you wanted to scout a neighborhood quickly or drop off tiny gifts no one could see in real time. That's not paranoia, that's simply how you would do it if you were good at this. Mars, especially, becomes the accidental lookout. While Earth is dazzled, Mars isn't. Orbiters on that side of the sun can track the visitor straight through the glare, log the brightness, watch for the stutter of fragmentation, and listen for any radio fingerprints that rise above the solar noise. The outer system fleet gets a shot too. A long baseline view from far away turns a tiny wiggle into a measurable shove. If there's a discrete thrust event, more than one camera will see the same kink from different angles. This is why the teams are calm, even when the internet isn't. The plan is boring because it has to be. Keep Mars awake, schedule occultations before and after, stack spectra, and let math veto the drama. The thing about secrecy in space is that it leaks into timing. If something deploys behind the sun, it has to cross open water to reach anything interesting. That travel time creates a telltale lull, and then a burst of new dots in places they weren't before. High-cadence surveys will rake the sky for those late arrivals. Unbound fragments arc away with physics you can model. Guided daughters take cleaner, Stranger paths. Add one more layer. Temperature. Real engines dump heat. Radiators glow. Coatings radiate at specific colors, even through the soup of solar photons. Thermal imagers can look for a hot patch that drifts like a component, not a sun-baked spot. If a thermal signature tracks the rotation like a bolted-on panel, that's not chemistry, that's design. None of this requires believing the wildest version of the story. It just asks you to respect the scoreboard of coincidences. A retrograde approach that hugs the ecliptic, a tri-planet tour, a speed that makes intercepts fantasy with today's rockets, a closest sun pass that happens while our home world can't watch. One of those is noise. All of them together demand better questions, and those questions don't stop at what is it. They slide quickly into what would we do. If the post-perihelion track screams capture, do we speak? Do we ping it directly, or let the outer probes and Mars keep listening in silence? The safe move is patience. Let the physics wash the hype off the timeline. If it's ancient ice, it will act like ancient ice under stress. Uneven brightenings, tails that finally obey the sun, a trajectory nibbled by sublimation, not sliced by thrust. If it's not, it will betray itself in cadence, a burn that starts and stops, a repeating glint, a harmonic in the radio quiet that doesn't belong to plasma. Either way, the next beats are already scheduled by orbital mechanics, and that's the edge you want as a storyteller and a scientist, because whatever happens behind the sun doesn't stay there. It ripples outward in the only currency the universe honors: timing, temperature, trajectory. And once that ripples reaches us, the bigger question we've been dodging steps out of the shadows, whether we're the only ones talking in this neighborhood, or whether something old has been listening longer than we've been alive. But that wasn't the whole story, because before we ever looked up for answers, we spent a century shouting into the dark.
Thought for 50. If you want to understand why 3IATLAS feels less like an accident and more like a callback, start with the noise we've been leaking into space for over a century, because long before we had a plan, we had a signal. December 1906 gave the cosmos our first unintended broadcast, and ever since, a balloon of radio and TV has been expanding at light speed, now roughly 200 light-years wide, a hollow sphere stuffed with game shows, war reports, weather bulletins, and carrier tones that no star or nebula would ever make on its own. And inside that bubble sit thousands of sun-like stars that have already had time to hear us, analyze us, and if they're curious or cautious, aim. The 1974 Arecibo message wasn't subtle either. A tightly packed data burst beamed toward M13 like a lighthouse wink, saying, here's our math, here's our chemistry, here's what we look like if you squint. And even though that target is far enough that we won't trade messages in any human lifetime, the act mattered, because it proved we were willing to speak on purpose, not just leak by accident. Add radar planet-sweeping pings, powerful enough to light up asteroids across the inner system, and you get an unmistakable signature of a species that went industrial, then orbital, then interplanetary, and every watt of that story rides on narrow bands, repeats with clockwork regularity, and cuts through cosmic static in ways a cautious intelligence would flag as non-natural in seconds. Which brings us back to timing, because if you map the growth of our radio bubble against the approach of Atlas, the timelines overlap in a way that makes your neck hairs rise. Our loudest century lines up with an object on a precision route that threads Venus, Mars, and Jupiter, and swings past the sun right when we can't look. And even if you chalk each datum up to chart, the stack of coincidences starts to groan under its own weight. The dark forest crowd will argue this is how you do recon in a hostile galaxy. Never declare, never chatter. Glide in along the plane where planets live. Let the star hide your engine work. Keep your thermal signature just below the threshold. And if you must talk,
do it in a way that looks like plasma noise, while the optimists will counter that physics alone can sculpt weird paths, and that ancient ice can act old and quiet until it does. But both camps quietly agree on one practical thing. Our broadcasts are a breadcrumb trail we can't unscatter, so what should we actually be watching for now that the breadcrumb may have been followed? Look for the kinds of echoes only technology makes. Narrowband carriers that drift like a disciplined clock, not a storm, polarization patterns that flip in ways plasma can't sustain, harmonics that arrive at integer ratios as if a transmitter is switching modes. And if the visitor truly wants a peek, expect passive tricks first, bistatic radar tries that bounce our own planetary pings off its skin, occultations that betray a shape too sharp for a rubble pile, glints with repeating cadence that feel like a rotating panel rather than tumbling rock. Meanwhile, the message we might choose to send is its own risk calculus, because a targeted hail during the inbound leg could be read as friendly curiosity or as sonar from a hunter. And the safer play, at least until after the blackout, is to keep listening with discipline. Stack the spectra from Allen, Greenbank, Meerkat, Lofar, and every dish with a spare nut. Cross-check for local interference, and pin any candidate to sky coordinates tight enough that another instrument can confirm or kill it within hours. There's a second layer too. Optical and infrared beacons, because a craft that won't speak by radio might still bleed heat through radiator. And if a hot patch tracks a stable axis through rotation instead of smearing like vented dust, that's design, not geology. None of this requires belief in sci-fi, only respect for information theory. Nature loves broadband, noise and chaos, while engineers love narrowband, repetition and efficiency. And when you see the latter peeking through the former, you take it seriously. The part that stings is that we can't rewind our century of shouting. We can only be smarter about what we add next. No panic pings during the eclipse, no vanity transmissions, just to claim the headline. Because the quickest way to turn a mystery into a mistake is to speak before you understand what's in earshot. So we wait with intent, ears open, math ready. Because if Atlas is nothing but antique eye, the universe will prove it by the oldest method in science. A prediction that matches the curve and a silence that refuses to break. But if something answers, if a carrier rises out of the glare with a drift that says clock, if a shadow crosses a star with edges too clean for chance, then our century of leaked invitations will have finally been accepted, and the next move won't be made by our loudest voice, but by our quietest question. And what happens when you send a golden record into that same dark, and the dark sends something back, is exactly where we go next.
Thought for six. So here we are, at the edge of the known and the almost knowable, staring down a choice that says more about us than about the things slicing through our sky. Either 3IATLAS is the wildest natural wanderer we've ever caught, an ancient thick disk relic with a speed that laughs at our rockets, a near solar skim timed so perfectly it vanishes behind the star right when we're blinded, a tail that points the wrong way because the grains are so heavy light can't shove them, or it's the first deliberate hello we've ever earned, a reconnaissance craft riding a precision track that threads Venus, Mars and Jupiter with odds so tiny you almost have to whisper them, and no matter which answer wins. Our world is different now, because if Atlas is just geology, it still rips open a door into the galaxy's deep time, a 14-billion-year-old time capsule that outlived its birth star and learned to surf gravity until it was fast enough to cross a solar system like a thrown spear, and that means there are more like it. Dozens per year hiding in glare and star fields. We rarely scan a secret traffic we're finally equipped to see. But if the other reading holds, if SETI's 21 terabyte listen, the weird tail geometry, the retrograde plane-hugging approach at 98 kilometers per second relative to Earth,
The blackout perihelion that's tailor-made for a quiet braking burn. The stacked close passes that look less like luck and more like targeting. If all of that points to intention, then the story shifts from astronomy to agency, and we become a species that went from shouting into the dark to learning the dark can shout back. Either way, the next pages write themselves in tests, not wishes. When the object re-emerges after its October 29 blackout, it should obey physics so closely we can pin it with predictions. Brightness curves that rise and fade like a seasoned comet's, spectral lines that speak water, COC and not alloys, a path that bends with only solar gravity and outgassing, not course corrections, noise that stays noise. If it breaks those expectations, if a narrowband carrier hums with a clock-like drift, if glints repeat with a cadence too clean for a tumbling rock, if occultations draw edges that look machined, if the trajectory changes in ways no vent can explain, then the conversation we've been practicing with plaques, golden records and century-wide radio bubbles turns real on a timeline measured in months instead of millennia. That's why the smartest move right now isn't bravado, it's discipline. Keep the dishes on it. Cross-check radio candidates across arrays. Map the coma. Watch for fragment release that looks like staging, not shedding. Let Mars and the outer system craft carry the baton while Earth is blind. Hold the urge to ping during the eclipse, because the loudest species in a quiet forest doesn't last long. We've already announced ourselves for 100 years. We don't need to spike the volume during the one window that hides everyone's hand. The bigger truth this visitor exposes is uncomfortable but empowering. We are detectable, we are curious, and we are finally good enough at listening to catch a whisper if one is sent. Our Arecibo moment, our Voyager messages, our accidental TV shell racing outward at light speed, those weren't mistakes. They were a promise to our future selves that when the universe answered, we'd have the tools and the nerve to hear it. Maybe the reveal is mundane and beautiful, an old mountain of ice and rock that teaches us how galaxies age. Maybe it's stranger, a probe older than our oceans, reading our spectrum, tasting our planets, and deciding what to do next. In both cases, the call to action is the same. Stay curious without being careless. Demand signals, not stories. Reward the people doing the measuring, not the ones selling the mystery. And if the data land on natural, don't sigh. Celebrate, because we'll have proved we can catch a ghost hours from the bright heart of the Milky Way and pull a biography out of its light. If the data land on engineered, breathe. Then do what grown civilizations do. Coordinate, document, communicate with caution. And remember that surviving first contact is more about patience than poetry. You've made it this far, which means you're the kind of mind this moment needs. Tell us what you think the cleanest test is. Tell us whether we should speak first or keep the channel cold and listen. Drop your city and your time so we know who's watching the sky with us. And if you want the follow-ups the hour they break, when Atlas clears the sun and the numbers stop guessing, tap subscribe so the next alert finds you. The universe doesn't often hand out endings. It hands out forks in the road. 3IATLAS is one. Whichever path it proves, we walk forward from here a little quieter, a lot sharper, and fully awake to the possibility that the night is not empty and never was.